Bonjour à tous et bienvenue à ce webinaire conjoint EcotoQ, Chapitre Saint-Laurent. Alors aujourd'hui, on a le plaisir d'accueillir Scott Smith, professeur à l'Université Wilfrid Laurier. C'est particulièrement un plaisir pour moi parce que je considère Scott comme étant mon jumeau scientifique, puisqu'on a suivi un parcours parallèle très similaire au fil du temps. Terminé nos études à peu près au même moment, commencé un poste, entrer en fonction comme professeur à peu près en même temps, et des intérêts très similaires, évidemment, sur notamment les métaux dans l'environnement. Donc, le sujet du webinaire de Scott aujourd'hui porte, bien entendu, ceux qui le connaissent, sur la matière organique dissoute et la biodisponibilité des métaux. So with this, Scott, pass it on to you.
Excellent. So yeah, I think I heard trace similar. So maybe Claude, you were saying that you and I are similar, maybe in terms of the work we do or our career paths. Either way,
exactly.
I always make the joke that Claude is my French twin, although I do have a twin brother. I like Claude better. So this is very nice. Thanks for the invite. And I know it's payback because Claude, I recently invited Claude to give a departmental seminar. But that's good. That's the way it should work, back and forth. It's excellent. So, I tried to think what to talk about. Claude said, what the audience would be. But other than that, I had free reign. So I kind of thought about some work we've done recently and how I could kind of put it together, kind of instead of talking about one thing for the full time, kind of talk about two different things that were linked. And it really, a lot of the previous work that we have done is related to metals risk assessment, on the chemistry side, understanding speciation and how speciation links to toxicity, and ultimately those toxicity numbers get interpreted in terms of setting guidelines or criteria. So a lot of the work we've done historically involved the biotic ligand model, which I'm going to talk about. The biotic ligand model is a really powerful tool for taking bioavailability and toxicity modifying factors into account, in setting a permit for a discharge or whatever. But the adoption of it is not, is sometimes limited by missing data. In particular, what's the organic carbon, where metals bound to organic carbon tend to be less toxic. So it's an important piece of the puzzle, and it's often missing. And so I'm going to talk about ways to estimate remote carbon remotely. So is one way to perform metals risk assessment when that data is missing. And I'm also going to talk about, skipping the BLM entirely, and let's just try to work on methods to measure bioavailability, wherever, we're interested in assessing metals risk. I'm going to list the co-authors at the end. I'm sure I'll mention their names as I go through, but I put the list at the end so I can make sure I acknowledge the people involved in the work. Plus, when I made this slide first, I hadn't really figured out exactly what to include, so I didn't know which names would be involved. Okay, so the next slide. Okay, so little background. A lot of you might not know Wilfrid Laurier University, so I pulled up the map, had a pin at my school and zoomed out. So, we're an hour and a bit away from Toronto in Southern Ontario, near the University of Waterloo, which is a larger institute. It's a nice picture, the kind of welcome sign. I like it because of the flowers, and we're getting to that time of year where we'll start to see flowers and green. So I'm pretty excited about that. So since I've been at Laurier, I've been here more than 20 years. It's moved towards comprehensive university. It was primarily undergraduate before. Now we classify as comprehensive. Over 100 years old, 20,000 people, 800 faculty. Over 100 of those are in the faculty of science. I wrote here last 10 years, push becoming more research intensive, maybe the last 15 years. They've really had that same coincident with the comprehensive university designation change. I mentioned Rick Plale. Some of you may have known Rick, who unfortunately passed away, but he was very significant in the early developments of the biotic ligand model. So from the perspective of ecotoxicology, he would definitely be our claim to fame, and just all around great scientist. We've only had a PhD program about the last 10 years. In terms of research priorities, not just in chemistry, but across the disciplines, there's a lot of focus on water, especially in cold regions. And we have a new 10-ish years old Center for Cold Regions and Water Science that I wanted to include a picture of this, and I wasn't on campus, so I went to Google Maps, and hit the street view. It's amazing, but that's our building there. A lot of this work would have been performed in here, not in the greenhouse, but I think the greenhouse is a neat feature that we now have. For me in particular, when I was just newly head of lab, I thought I had to come up with an acronym, and I never used that acronym because I just come up with it, and I was at, I think, CTAC conference, and there were a group of professors sitting around making fun of the young professors who immediately come up with acronyms for their lab. So I rarely use it, but it is convenient to have, and it does summarize what I do. So Chemistry Laboratory for Environmental Aquatic Research. And my wife actually came up with the acronym. She's clever with things like that. And it does, it summarizes what I do. Aquatic geochemistry, mostly metals and nutrients. I do mostly applied science. Of course, I have my discovery grant, but I really like to make a difference in terms of the career and to have whatever impacts, even if small, in a tangible way, to improve water treatment. I do a lot of work on phosphorus removal and recovery. And then on the metal side, which I'm going to talk about today, that link between metal speciation and toxicity. Organic matter complexation is one of my favorite things to study. So I want to talk about the biotic ligand model. I actually made these pictures in my class to explain it to the students, and I suspect most people on this call know what it is, but it's nice to hear me say what I think it is, so we can make sure that we're on the same page. So these are made up data, but the x-axis is the total metal and fraction survival, so made up toxicity data. And so the black dots are water that's no DOC and it's soft, and so that's our kind of reference, clean lab water. And then we add some DOC, and those gray dots, we see there's a protective effect. And then we add hardness as well, hardness cations, we get an even greater protective effect. So this is kind of what we're dealing with. We know that there are toxicity modifying factors, and that the EC50 is not a fixed value when considered for different samples as we change the total metal. So if we express it as a free ion, we get to the free ion activity model, FIAM, and that's great. It collapsed, the bioavailability, in terms of expressed as survival for the DOC, for the complexation, but free ion activity doesn't take into account the fact that competitive effect, the protective effect of hardness, calcium and magnesium cations. So then we get to the point where we change the x-axis to metal accumulation at the biotic ligand. And now in my simplified little made-up data, we see they all collapse. And so we're taking into account the competitive effects, the complexation in solution, and ultimately then we can predict toxicity when we state that it's proportional to the metal accumulated at the biotic ligand, which a lot of times when we're talking about fish, we say it's the fish's gill. For DAF, we tend to say it's the whole organism. So here's the very famous picture of the biotic ligand model, which actually took this out of one of Rick Plale's presentations from years ago. That little F, we were working on quality factor, which is a lot of work that I've done in the past, is to see, is it enough to just input DOC, or do we need to modify DOC for the specific molecular nature? Anyway, this is I wanted to put this picture in just because I feel comfortable seeing it, but I think we all kind of see or understand, here's the biotic ligand model. And so we need inputs to the biotic ligand model if we're going to use it for ultimately regulatory needs. So we're going to need all the cations, the strong base cations, strong acid anions, major cations and anions, and we're going to need DOC and pH in order to then predict the metal accumulation at the biotic ligand, and then that could be converted, by independent measures of toxicity that calibrate the data set, and we can say how much accumulation leads to what toxicity. And this is great and is a tool that is used definitely. Permit writers will use this in order to set criteria for different polluters, but it does require information. It requires the DOC to be measured. And DOC, it actually surprises me that it tends to be, of all the parameters involved, calcium concentration, magnesium concentration, pH, those things are routinely measured, but the DOC is not. And so DOC can be a data gap. And so that could be filled by, regression analysis, fill missing parameters based on other parameters. There's different strategies of reduced BLM with fewer parameters, but really at the end of the day, DOC is really the DOC and pH are the most significant variables in terms of what's the copper criteria or whatever the model's going to estimate. So BLM application can be limited. So maybe it's just because there's no TOC machine at the labs that are doing the work, or maybe the locations are difficult to assess. And so that's where I put this work together. We can use remote sensing to estimate the DOC. So I'm going to talk about that, call it part 1. And part 2, can we measure bioavailable metals directly? And there's other methods to do this, ion selective electrodes, which we've done, and I like quite a bit. Or DGT, passive samplers of different kinds. I'm not doing a review of the different methods. I'm going to talk actually about our recent work using DNA in order to estimate metal bioavailability. Our progress, we're not done, but we're working on it. All right, so the remote DOC part. Remote methods, have a lot of advantages. We can do more frequent measuring spatially and temporally. We can do remote sensing using a drone. So that's kind of you're on site, you're flying the drone, or we can use satellite-based methods. The satellite methods, obviously the satellites are passing around taking the images so we can get, those snapshots versus time. So it's really a powerful idea to kind of fill that missing data gap for DOC, but there's 2 questions. This hadn't really been done a lot before. There was enough information that it was promising to pursue, and we got funded to do it. But can we convert those remotely sent signals into DOC? And then so that's the part that was done actually at ENRS. Karen did that, and I acknowledge him and his students. I acknowledge him at the end of the talk. I'm going to share those results. At Laurier, we looked at how accurate do these DOC estimates have to be to get useful BLM estimates. So if we measure DOC and it's off by a factor of 1,000, obviously we're not going to be able to use it. So what factor kind of uncertainty can we have in that estimated DOC in order for it to be useful going forward for BLM estimation and ultimately metals risk assessment? So this is my vision long term. So this is just a fun little cartoon. So I took a map, again, Google Maps. It's amazing what you can do with Google Maps. This is actually near my dad's place near Sault Ste. Marie. I thought I'd pick a place where I know there's a lot of lakes. So you can imagine here's our lakes, and then the satellite goes by. We estimate DOC. As well as the other BLM parameters. And then we can kind of map that area and say, the green location, those green lakes are safe, and that you could develop mines or whatever, whereas the other ones, they're going to be sensitive because they don't have enough DOC or the pH or whatever. So I think it's kind of a powerful idea to just think about, and I don't know what spatial scale, this was just as a picture, but the kind of where are the safer areas and where would be the more high risk areas. But in order to have this as a long-term goal, we got to do those other questions. Can we measure DOC, and how well do we have to measure DOC? Okay, so we had, I'm just going to talk about the drone-based methods. I'm not a remote sensing person. I think I understand this well enough to talk about it. I'm excited by the results. I'm not going to talk about the other things because it's obviously not talk on remote sensing. So picture the drones, they would fly along a transect, and then we would have a boat, follow that same transect, collect samples in order to measure the DOC in those samples. The drones had fancy cameras on them that measured the reflected light. So here's a picture of the drone. We actually didn't participate in this sampling event because it all happened during COVID, and traveling was an issue. Like even to be in the car with my student, there was rules against that. So we didn't get to go, but they sent pictures, so it was nice. And I think the drone looks absolutely amazing. There's the operator flying the drone, so you can see that off in the distance. And then there's, like I said, a transect. And I don't even know who these people are. Maybe you guys have seen them because I assume at ENRS. And so they would follow that same path and collect samples that the drone had already or simultaneously mapped out. So it was done at 3 different lakes. This was an early part of the project. I just happened to have slides that summarized it. So they did that at 3 different lakes. This is a picture of Lake Magog. And this is what the data looks like. The actual measured data is that L sub lambda, so that's what the camera is measuring. And the other parameters there are corrective terms for spectral interferences. Again, I'm not a remote sensing person. I certainly trust Karem and his students in order to do a great job at that stuff. And so that's what the original data looks like. Wavelength and reflectance at all these spots across a transect where we simultaneously had measured DOC. But what to do with this data, and that's where it's impressive what they can do, is they test different processing of those reflectant-based measurements. And this is a map of basically functional relationships between parameters, so these different indices, kind of on the X and the Y, and the color map is how good the correlation is. So the R squared, values, over 8 in the yellow, and the dark blue, not good correlations. So we then were able to pick from that where the brightest spot is, and so that's the best way to process the reflectance data, and it happens to be the reflectance at 777 minus 7023 divided by 77 plus 723. Honestly, it's a fascinating thing, that all this testing could be done in order to determine all these ways to process the data. What's the best way to process the data? At the end of the day, when that reflectance data is processed in that way with these 777, 723 index, we see this relationship between the index and the DOC value. And that's great. That's what we need. We need that in order to be able to predict the DOC ultimately in unknown samples. So this is a calibration data set. And you can see that it works quite well. We have our measured DOC on the x-axis and our y-axis, the estimated DOC determined from remote sensing. And certain, if this is something that interests you, I can put you in contact with the co-authors. I think it's quite exciting, that we're able to do this. But we look at this, and if we were doing experiments in a lab and we get a nice R value 0.88, we're going to be, oh, good. This is a good fit, but is it a good enough fit? And that's the question that we did Monte Carlo analysis at Laurier, and so we ran the biotic ligand model. So this would be the windward biotic ligand model. We got a copy from Bob Santor for research purposes that we could go in and we could manipulate, and we ran the model multiple times where we varied the inputs. We did a lot of this. We did, where we varied all the inputs, so the major cations and anions, pH, and the DOC. It was a really cool project, which we wouldn't have done if it wasn't for COVID, because we were just looking for a plan B at that point. And so we had a lot of insights, into, how the BLM performs and the significance of the different variables. But focusing on the DOC, how good an estimate do we need of DOC in order to be good enough? And what's good enough? Those of you who do BLM things on a regular basis, they always talk about this factor of 2. We want our predictions to be good within a factor of 2. So a factor of 2 above and 2 below, so kind of a range, 4. So that's, and I told the student that, and I said, you got to find this written down somewhere. We can't just say that's what everyone says at conferences. And we did find, we found a citation for that. So that this factor of 2, is cited. So we want to predict within a factor of 2. So how good does the DOC have to be? So this is a little map of that. So if their error is 1%, you can see we're within that factor of 2, those dashed lines. If the error is 10%, we're within the factor of 2. 25% error, a little bit of our data is now outside that factor of 2. So we did this kind of systematically, and we got to the point where we're saying basically 20%. So if our DOC error is within 20%, our BLM prediction error should be within that factor of 2 above and below what the true estimate would be. So this just allows us to put kind of constraints on how good a job the remote sense DOC has to be. So for that initial calibration set, we didn't do too bad. There were 9 out of 13 points were within that 20%. This was a early part of the project. It actually got better and included the satellite images as well. So that's what this data shows. So I'm not going to go through how the satellite stuff was done because I haven't read up on it. I don't remember off the top of my head, but the UAV, that would be the drone. So the open circles, and that's the performance, with only a couple of points outside the 20%. And then also Landsat satellite and Sentinel-2 satellite. And we were able to get really good estimates of DOC for a range of lakes. And I'd have to go through the original report to look up what lakes that were done. Lakes tending to not be very far from the NRS, because that's where Karev and his group did their work. So this is very, very satisfying, and I hope that gets picked up, and that people start to explore even further what's possible in terms of estimating DOC using remote-based methods. Okay, so the next part is to talk about sensing metals, or metal sensing using DNA. I hope the slide's not, one on my screen's a little bit cut off. I think it's probably cut off for you guys too. Anyway, hopefully that doesn't happen for all of them. So there, like I said at the beginning, there are a lot of ways potentially we could measure bioavailability directly on a site, in a effluent that we're trying to regulate, to set a permit discharge limit for. Ion selective electrodes are one that I like. There's other voltammetric methods that have been shown. Passive samplers, so DGT, jellyfish. These are all possibilities. Using DNA is another possibility that might have some advantages. Certainly the electrochemical methods can sometimes, like in situ voltammetry, and that can be fairly difficult and involved. The DNA line, has a lot of potential because it's cheap, easy to use, but easy to use in the lab. And we're a while away from saying, can we go and use it in the field? But before we go to the trouble of really developing a field-based method, and there are strategies, you can anyway, I won't go through that, but there's possibilities of how to make this a field deployable method. But we better make sure that in the lab that it works and does respond to bioavailable method. Here's a little diagram that shows, before I talk about that, I got the idea for this project as I was at a presentation, they were showing really amazing performance for lead, rare earth elements. I think even small molecule, I forget if it was salicylate or what it was. But a diversity of things that they were able to sense using these DNA enzymes, not always with fluorescence, as we're going to discuss here, but as a strategy for analysis, quite impressive. But their calibrations always were versus the total metal, and they were always done in lab-based samples. And so, of course, you can already look at this diagram and see that the metal has to interact with the DNA in order for the sensing to occur. So what form of the metal is going to interact? And as a geochemist, thinking about speciation, wondering, are there specific forms that will interact more than other forms? And in particular, if it's bound strongly to dissolved organic matter, that stuff that's not bioavailable, should it give a decreased or no response to the DNA enzyme? So that was what kind of, and then, so would the response be proportional to bioavailability? So that was kind of the impetus for this. And you know that if they've fixed water chemistry in their lab-based solutions, all the species, lead 2+, lead OH, lead chloride, lead acetate, they're all going to covary. So that's, you can't just say that it's the free ion that it's sensing or it's lead hydroxide, because the ratio, or all of them will increase linearly as you add total lead, unless you exceed the binding capacity in solution for one of those things. So that's where we had to do kind of systematically look at this DNA enzyme from a geochemical perspective. Anyway, exciting technology, and a good reason for us to pursue it. The basis of it is you have this kind of DNA strand here with the RNA, and the lead, because of the DNA, lead in our example, will come in and cleave the RNA. And so there's two steps. There's the lead cleaving, and then the fluorescent fluorophore leaving. And that's what that little red thing and that diagram indicates, is that the fluorophore goes off into solution, so we can measure a rate of increase in fluorescence signal in the presence of lead. The little loop here, I don't know if you can see my mouse, but the little green circle kind of at the bottom of the DNA, that's the part that changes depending on what metal you're sensing, or anion, or whatever it might be. So that's done with kind of those large kind of library tests where they expose all these DNAs to the metals and look for the bright spots. It's kind of determined experimentally in order to determine what loop corresponds to what metal. But there is good specificity. Kevin, I saw you joining the call. I got a slide in here that you'll be interested in terms of specificity, and certainly not as absolute as my student presented it at the conference on the weekend. All right. Okay, I think I rambled through a lot. I hate text on slides, but I put it there because I want to make sure that I go through a kind of systematic way and say what I want to. But I think I already said it all. So we got our DNA that's specific for the metal. We get the cleavage of the RNA. RNA is fluorescence tagged, so our analytical signal is the fluorescence increase. So it's a kinetic assay. The rate of fluorescence is the signal. A lot of people do it different ways. They'll take the initial rate, the slope of the curve. Because I like fitting data, we fit it to a nonlinear regression model and determine the first order rate constant. So we're hypothesizing that the DNA-based metal signal would correlate with metal bioavailability. And so far, we've shown that it correlates pretty well with speciation, and we're in the process of doing experiments to compare it to bioavailability. So yeah, I'll talk about that last point in just a second. This here I put in for Kevin, but even everyone can pay attention. You don't have to go to sleep. The question of how specific is the DNA enzyme, GR5 in our case, to lead. And yeah, the student on the weekend said it won't respond to anything else, nothing else. And no, that's not true. And of course, as chemists, we know that, that there might be a lot of specificity, but there's going to be other divalent cations are likely going to interact in similar ways. And so this graph here shows, the red is the 2, and this isn't our data, I just looked this up. 2 micromolar lead gives a good response, all the way down to a signal of 25 nanomolar lead. The same setup done with zinc, 1 millimolar, 500 micromolar, so much higher concentrations, but you do see a signal from zinc and a signal from copper, pretty negligible signals from the other metals that were tested. But certainly, yes, you can get interferences from other metals. And so it's something to keep in mind, but it is highly specific for lead. So we prepared a lot of samples spanning a range of pH, DOC, and electrolyte composition, and we measured the first order rate constant. So this is what the data will look like. So versus time, and for different colors indicating different total amounts of lead, we measure the fluorescence in a plate reader. So we have all the plates and we measure it simultaneously. So you can see that blue for no lead, that's a nice flat signal. And by the time we get to 1,000 nanomolar lead, we get a rapid increase and the curve is flattening out. So we fit that to that model at the bottom there as a function of time, and we can determine where will the curve flatten out. So that's that F infinity. That doesn't tend to be a good parameter for calibration. We tested it. K-obs, the first order rate constant, works much better in terms of calibrating the lead response and getting straight lines as we expect. So here's the list of the different samples that we worked on. So we made up all these different samples. So you can see different pH, 6.5, 7.5, and 8.5. So there we're trying to vary the lead and the lead hydroxide formation. I forget what the first hydrolysis constant is for lead. Maybe it's around 8. Certainly we have by 8.5 samples, or sorry, the 8.5, we have appreciable amounts of lead hydroxide as the component of the lead that forms. We really wanted to test that, number one, because we want to see the pH sensitivity or range that the method could work, but also because some of the theories in terms of how this cleavage reaction happened involve the metal hydroxide. Specifically, it's the metal hydroxide that does cleavage in some of these proposed mechanisms. So we wanted to see, if the response in terms of pH, where lead hydroxide would be a significant species. DOC from 2 to 8 milligrams per liter, and then sodium acetate often as the electrolyte. That's the most common one from the literature, but also sodium chloride and sodium bicarbonate. We have some other ones. This data is already cluttered enough where we did sulfate. And yes, that's a good description of what we did. And so here are all the data, so the observed rate constants for all those samples. You can see a tendency as we get up to the micromolar amounts of lead for a higher signal, but certainly this would not be useful as a way to calibrate and determine lead. So if nothing else, we showed that for environmental monitoring, which these DNA signs have been proposed for, they better take the solution composition into account, that there is definitely an influence of DOC and pH and electrolyte on the signal. If we go back, here's want to make sure I get this right. So that top symbol, the diamond, you can see that the diamond symbols there kind of across the middle, going up and down, but with no trend. So that's the sample with DOC. So we varied the DOC in that sample, and there was no increased K-obs response. And that's a general thing that we do not see. If we have a sample where the DOC is present complexing the lead, we don't generate a signal in K-obs. So how do you handle all this data? We've got a lot of data and a lot of variables. So we do multiple linear regression. We do it on the log of the observed rate constant, and we tested all the different species that we had. So we ran cheeks. I'm sorry, the slopes got cut off, but I remember what the number is. We used cheeks to calculate speciation. It has an implementation of WHAM version 7. I prefer to use cheeks because cheeks also includes precipitation, where the WHAM you would get from Ed Tipping and Steve Lofts doesn't include precipitation. So we wanted to be able to make sure we weren't super saturated when we did these things. And so we had all the different species of carbonate, but soluble species, carbonate soluble species, and the DOC species. Not shown here, we also tested the sulfate species, and we just fit the slopes, what slopes could we, the minimum number of slopes that we could use in order to reconstruct the data. And we found we only needed these 3 species. We needed lead 2+, the ionic form, lead hydroxide, and lead chloride. The slopes, 0.9 for the lead 2+. The one that's cut off there would be the lead chloride, and it was about the same. I think it was 1. So the lead chloride and the lead 2+, very similar in terms of their sensitivity. But interesting, the lead hydroxide was more than 10 times more sensitive. So it really highlights that pH is a significant variable in terms of interpreting these measured KOBS values. Now, what's great when we've done all this calibration is that we can go turn around and see, well, how good an estimate will we get of lead 2+ from all these samples. And so we just rearrange that equation, solve for lead 2+, and then we can plot it versus the predicted value from WHAM. And pretty good. It's on a log scale, sure, but there's definite, I think it's cut off here, but the R squared was 0.88. And so we get a decent ability then, in theory at least, to predict lead 2+ directly from the KOBS value that we would measure. Now this is a little unfair. This is a proof of principle. So we used the data, calibrated it, and then turned around and got back what we put in. So it just shows that it's possible. We could certainly go and measure unknown samples, use the same calibration line, and we would get estimates of lead 2+. The thing is, I forget how many samples with replicates we did in this set. I think it was 48 samples altogether. You can't go and measure 48 samples as your calibration set, over the space of several days, and then go measure your samples. So although this is I feel is a good proof of principle that there is potential for this DNA zyme to be used in sensing technology, we still got some method development to do. I'll talk about that. Okay. So I'm gonna summarize now. I would say both methods show promise as a kind of alternate strategy for doing BLM based metals risk assessment, or not always BLM. The DNA zymes aren't actually BLM, but let's say bioavailability based methods for metals risk assessment. Remote sensing, we did enough work that I think it shows promise. And I hope that someone would do more work on that. Someone who knows more about remote sensing than I do. The next, we were looking at this DNA technology to see is there at least possibility. And yeah, we're very comfortable in saying that it's responding to the species that we would tend to think of as the bioavailable species. In particular, it's not responding to the organically complexed lead. So that's good news. So it's responding to some set of inorganic, including lead 2+. And so we're working on now measuring our KOBS based lead in bioaccumulation experiments with Daphne, and to see will the signal we get from this instrument predict bioavailability or bioaccumulation across a range of water chemistries. So we're working on that now. The physically deploying these sensors, it's done on a plate reader, in the lab. We're not going to take a plate reader out to the field, but we could do stuff with different gels in order to collect the samples and kind of separate them, or microfluidics. There are ways that we could do it, but the big hang up or hold up in my head still is, how do we calibrate this thing? And so far we've shown that this depends on the lead hydroxide and the lead chloride. So you could imagine doing multiple linear regression, having we're going to measure the K-obs, but to measure chloride for input to the equation and pH for input to the equation using just standard ion selective electrodes, glass pH electrode and a chloride ion selective electrode. You'd have to measure calibration standards, and we got the 3 slopes to determine. So I don't know, 6 or 9 standards would have to be measured. It's possible. The complication here is that, and I didn't go into this, but the DNA enzyme itself, the fluorescence that we get from lead is dependent on the ionic strength of the sample. So if you do a artificial seawater or freshwater, the slopes, the calibration is going to be different for your lead response. So then we have to do matrix matching in terms of preparing our standards so that the standards have the same electrolyte composition as the sample. And we can certainly do that. There a lot of methods work based on matrix matching. My hope is that we can do standard additions as our calibration method, so that the sample itself would be used to calibrate. To do this, you would add enough lead to saturate the ligand, the DOC, and then our response from that point onward would be bioavailable. And we would get a linear response, which we would use then to calibrate the sensor and determine what the measured values for bioavailable lead were in the nonlinear region. And we've had some success with doing that. It just seems to be that to add high enough lead in order to saturate the DOC, we get to a point where the rate of fluorescence is too fast for us to be able to estimate it. But our way to correct for that is to add more salt. So we may have a method where you have to salt up your samples, and then do standard additions. So there's still a lot of details to sort out, but the exciting part is that, yes, the DNA enzyme response is speciation dependent, and it seems to be responding to the species that are more useful in terms of potential to estimate bioavailability. All right. So acknowledge, the funding for the remote sensing stuff was a CRD grant with International Copper as the main partner, as well as International Lead and Zinc, Nipira Tech, and Windward. Windward provided us with the BLM software. The DNA enzymes were funded by Global Water Futures. So yeah, I was aiming for 45 minutes. It says I'm 43, but that's not too bad. My final thank you would be to Claude for the invite. This was a pleasure and really fun to talk to you guys and to put this stuff together into a little story that I hope you found at least a little bit interesting, and I look forward to getting some questions. Thank you.
Thanks a lot, Scott. I'm going to ask people that want to ask questions to raise their virtual hand so I can see them popping up in my list, or either turn on their camera. In the meantime, I have several questions, and one that I really wanted to ask you is about the DNA enzyme. In the calibration, you have M1 was 0.9, so that's the weight of the free lead.
Yep.
And then M2 is the weight of the first hydroxyl complex, which was 16.
Yep.
So I understand this is purely empirical, but thermodynamically, that seems a bit counterintuitive, since that would mean that the first hydroxyl complex is about 20 times more, as an affinity that's 20 times more important than free lead. Did I understand that correctly?
Yeah, but it actually I can find the paper, and I don't know how much in your past life you had to deal with electron pushing mechanisms, but these organic chemists, biochemists use these things, and they draw little pictures of the complexes, and they kind of shuttle the electrons along in order to have the cleavage happen. And the one mechanism says that it's in terms of kinetics, so it's not a equilibrium of the binding strength, it's the kinetics that the lead hydroxide would go faster.
Okay. My intuitively, I thought, well, maybe it's a proton effect, because you have some of your calibration solutions are at different pH, or test solutions of different pH. So if you have more protons, you have less lead hydroxides, but you also have less competition between protons and free lead.
Right.
Have you tried to see if that would fit?
So put in like a
protons as competitors instead of having a component of hydroxyl complexes?
No, I didn't try that, because I just kind of thought, how can we relate it empirically to the species? But that's not a bad thought. The only thing, I try to think of these things. So if you were doing normal colorimetric or fluorometric analytical chemistry, you would form a colored or fluorescent complex. That's not what we're doing. And I think the interpretation like you're talking about is kind of assuming that's what we're doing, but it's the rate that the fluorescent goes up. And certainly the metal has to interact. So it has to bind, but that's not the end. It's not like we're sensing a lead ligand fluorescent complex or a lead hydroxide fluorescent complex. It's the release. But certainly mathematically we can put in proton as a competitor and see. I bet you it would describe the data as well. I mean, also, I don't know if it would be the same statistically, but I think that would work, because they're going the right direction. So yeah, it's more of the kind of mental picture of how to treat it. I do think lumping the species together, like testing what species kind of statistically correlate with the signal, is more useful than the proton competition, just because we don't have any reason we want to estimate proton competition. But at the end of the day, the only species, if you told me pick which species you care about, I would want lead 2+. So maybe using your proton competition idea, we could kind of just narrow it down to getting an estimate of lead 2+ directly. Kind of assume lead 2+ is the sensing species, and then correct everything else for that. So that's not a bad strategy, and it's the beauty of having the data, is we can explore alternate strategies. So this was a rewarding experience already, but that question, I love it. It gets the little brain going. So thank you very much, Claude.
I see two questions, but just a follow-up question from what you just said. So if you have non-specific binding, would that release the DNA zyme? Would it activate it, or just prevent the lead from activating?
Yeah, I think it would just prevent the lead from activating.
Okay, so you get no signal.
Right.
So a decrease in rate. Okay.
Yeah.
I don't know if it was Anne or Kevin who was first, but I'll go with Anne and then Kevin.
Hi, Scott.
Hi, Anne. It's been a while.
Yeah, it has. Yeah. Thanks for the talk. It was very interesting. It's a follow-up question of what Claude asked. Do you know if that DNA zyme is sensitive to pH in terms of activity, and if the hydroxyl complex, the fact that you see is more of a decreased or increased catalytic activity with the pH.
Yeah, so that's very, very similar to what Claude is asking, and it could be, but that's not the way I decided to interpret it, because I was kind of biased by what I thought would be useful to pull out of this. Same thing. So the all the work that they do, the lab-based work, it's always very well buffered, and they get beautiful responses. Change your buffer pH, you still get a great response, but a different slope. Is that the difference, in just how the DNA is behaving, or is it a difference in the speciation? I would say we don't know, so I interpret it as a difference in the speciation, but I'm going to redo the math and interpret it as a difference in the DNA with the proton competition. Because the other related thing is your nice clean lab-based solutions, you would do it in a fixed electrolyte. Fixed electrolyte, fixed pH, beautiful linear response versus total lead. And we do know that the conformation, the shape, not literally folding, unfolding, but that same kind of idea of the DNA and the RNA is, salt dependent. And definitely, there's no way for me to interpret that in terms of speciation. The activity corrections are too small, to account for the large differences we get in terms of, the salt influence. And that's what's kind of limiting in terms of the calibration. So either we have to do matrix matching where we have a fixed salt, and we could also do matrix matching where we have a fixed pH, do our calibration, and not worry about what species, just say we're going to call this bioavailable, and then what we still need to do is those tests with the Daphnia to confirm that that signal would be bioavailable. But long term, you don't want to have, if I kind of get ambitious in my head, and I think I want a sensor that will always work, and so we need to figure out how to calibrate it for all samples, not just matrix matching an individual sample. Yeah, great question, Anne.
Thanks. And do you know if there's some DNA enzymes that are specific to other divalent metals, or is it just that one for lead?
Nope, there's lots of them, and my excuse me, collaborator on this, we used to talk about nickel, and he said, well, there isn't one for nickel, but we can find one. He never ended up doing it. We didn't get funded to do anything like that. But yeah, it's surprising how many there are. Lead is one that used the most because it's really got such great selectivity, but it's also been improved, from the original one that was discovered, and they've iterated it to get it even better and better. It's amazing what they can do. It's not that expensive. You just send the sequence off, and they send it back to you. So we probably, for the experiments I showed here, we're probably $100, $200 worth of DNA, which is astounding to me, because I can't make DNA. Well, I guess I can make DNA, but I can't make it for lab use. But yeah, so if there's anything in particular you're curious about, I can see if I can find anything or talk to my collaborator about it. But this was our kind of, if it shows potential, could we do it with other metals? I know there's copper and there's silver, and those were the next two that I was thinking of doing. In particular, I mentioned I want to do calibration with standard additions. I think because silver binds strongly, it would saturate quicker, and that we might be able to calibrate without getting outside the linear range of the sensor.
Okay, thanks.
But yeah, they also have them for anions. It's astounding.
All right, we have questions in the chat. First one from Kevin about whether fluorescence of the DOC can interfere with the fluorescence of the sensor.
Yeah, it's a great question. And Kevin, I forget the wavelengths, but it's way outside the range where DOC fluoresces. And yeah, of course, we tested for that.
Even though DOC fluoresces over such wide wavelengths?
Yeah.
Yep.
Like it And it's also the DOC fluorescence, so it might contribute some to the background, but it doesn't change. And we're measuring a rate of fluorescent increase, and there's no mechanism that the fluorescence of the DOC would increase or decrease at the fixed wavelengths. So yeah, there might be some small amount of signal from the DOC, but it's not a changing signal. And so we measure the rate of increase in fluorescence. So we're good.
Can I ask a follow-up?
Sure.
So it's a much more general question in that I'm always intrigued that where the techniques that work well are using the optical properties of DOC, but we're trying to estimate metal binding, which really have nothing to do with the aromaticity of the DOC. It's something different. Can you give me your feel for that? Why does it work so well? Why should it work so well? Is there and could there be other, maybe perhaps better ways?
That's a fun question. So I had a PhD student, Hassan Al-Riesi, with Chris Wood, and Hassan was doing a lot of these optical parameters and relating it to protection. And we did an improved lead BLM based on fluorescence or SAC, I forget. That's satisfying, nice, and we accomplished something. But you're right. Lead is not binding to color, or to fluorescence. So I had Hassan do these acid-base titrations, because to me, acid-base is a great way to look at reactivity. Protons and lead, they bind at the same places, so the pKa values and the capacities are going to be useful. So for all the same samples that Hassan had worked on, and we found the relationship between SAC and the effect concentrations, we had titration data. Now, this was quite overwhelming because there's so many binding sites found in the continuous type of analysis that we did. So I kind of thought, well, why don't we think about really strong binding sites the way they do in WAM? So they think of tridentate binding sites. So I kind of divided the pKa values up in a way and came up with a ratio that I said this is related to tridentate metal binding. That you basically, with citric acid, the three would go together. And so I called it the proton binding index, or maybe Chris Wood named it, I forget. And that showed a really good relationship with color. And then, we were able to say that the metal binding was related to this kind of proton binding index. So that was neat. And it, just a small little thing, but it kind of linked reactivity to color. And if you think about, and I don't know if you teach first year chemistry, but when we teach about pKa values, and so if you do the pKa of this acetic acid, compared to the pKa of benzoic acid, the benzoic acid is going to be more prone to lose the protons because the anion is stable. And so I think that's why, and so we could talk about the same things in terms of metals. I think that's why it's the color and the fluorescence are rated to aromaticity, and the metal binding is also related to aromaticity. Because those functional groups, like a salicylic acid binding group, is going to be way stronger than some non-fluorescent carbohydrate dangling somewhere. So I think that's why. But it's a great and a fun thing, and like you say, it's bigger picture than what I talked about here. But yeah, why do we measure the optical things? Because it's easy. Great question, Ken. I hope my answer wasn't too rambly, but I thought about the same thing.
There's the last question from Dominique Ponton. It's about the first part of your talk, Scott. Yeah. He's wondering if the type of organic matter, autochthonous versus allochthonous, influences the remote sensing.
Yeah, so that's a great question, and that was one that we were going to ask in the original proposal. We were going to go on site and do field work, but like I mentioned during the talk, COVID prevented that. And so as it is now, we've completely ignored autochthonous versus allochthonous. And I would say that the lake selection tended towards the allochthonous end of the spectrum. I don't have specific measurements to back that up, just based on where the map and where the things were collected and the size of the lakes. So I think that's a great follow-up question. Would I expect it to make a difference? 100%, I would expect it to make a difference. Based even just we're talking about with Kevin, SAC 340s, that absorbance, the darker organic matter is allochthonous, the lighter organic matter is autochthonous. I really do think it would affect the reflected light as well, and that we would have to have different slopes or somehow take into account the nature of the carbon, or just to ignore it and hope that we're still within that factor of 2. But yes, it's a really, really good question. I'm glad, a little bit talking about the remote part of the talk. I feel like I should have just focused on the, or maybe I explained the first half better, and so that's why I had fewer questions on it. Anyway, thank you all so much. This was very, very fun for me.
Thanks, Scott. Dominique, did you have a follow-up question or?
No, it's perfect. Thank you.
Thanks.
Thank you so much for the talk.
Thank you all so much.
Yeah, thank you, Scott, and thank you everyone for participating and attending this webinar. We're right on schedule. And if anyone has any other questions, I invited to contact you directly, Scott. And I'll send you my own list of questions I had written down.
Excellent. Oh, that's what's fun for me. Thank you all so much. Have a great day.